Yo, welcome back. If you hear some sizzling in the background, it's because we're making bacon at the moment. Uh, all right, let's rock and roll. So today we're going to talk about differentiability. So what does it mean if a function's differentiable, and how does that compare to saying a function's continuous? We have to kind of distinguish between the two now. So we can start by first kind of looking at this informally. So when we say that a function is differentiable, informally that means that the function is smooth, right? So there are no jagged corners or turns. It's a smooth rolling function. And informally, we know that if a function is continuous, that means we can trace without lifting pen. But what would a more formal approach mean? What does it mean that a function is differentiable? Well, hopefully you're saying there's a definition for the derivative, right? It means that the limit of f of x plus h minus f of x all over h as h goes to zero, right, for any value x, it means that this is going to exist. Now, keep in mind, this is a limit, so it's a two-sided limit. There's a limit as h goes to zero from the right. There's a limit as h goes to zero from the left. So in a sense, there are these things called one-sided derivatives, which we're going to talk about today. And I actually showed that a little bit in the symmetric definition video. All right. What does it mean formally about continuity? Well, that means that the limit of f of x as x goes to some value c, right? So the two-sided limit as x is approaching c is actually going to equal the functional value at c. So when we see the words differentiable, we informally think smooth and we think, all right, the definition of the derivative exists. As opposed to when we see the word continuous, right, we think we can trace without lifting up our pen, right? But we think this definition of continuity. Now, does one imply the other or vice versa? And we're going to talk about that in a little bit, not just yet, though. All right, so let's start this conversation off by first talking about common points of non-differentiability. So points where you can't find a derivative. So it should be clear that in the examples I'm about to give, you can't really draw in a unique tangent line at any of these points, but there's formal algebraic or calculus-based reasons for why they are points of non-differentiability. So we start with a point of discontinuity. In fact, you always start with that. This is something you always check first. If you are discontinuous, then you cannot be differentiable at that point. So now don't let this little x naught, this little x subscript 0 screw you up. Instead of using little a or little c, we're getting fancy when using x naught. It's the same deal, right? So for some x value, if you are not continuous, so I happen to show a jump discontinuity here, but it could be a removable, right, or an essential, it doesn't matter. If you're not continuous, then you cannot be differentiable. So how do you know if you're not continuous? When you do this definition here. If the limit of f of x as x goes to that x naught, if it's not equal to f of x naught, well, then you're not continuous. This is something you always want to check first. All right. Here is another example of a point of non-differentiability. Like this thing here, yeah, that's a point of non-differentiability. So I can trace this without lifting my pen up. So it's continuous here, but there's no derivative there. It's almost like if you were to try to draw in a tangent line, it would be like a little seesaw, like weeble wobble on that point. In fact, you can't draw in a unique tangent line there. Now, how does this play out? Well, it turns out that when you do the definition of the derivative, right, that limit would not exist. And specifically, the limit as h went to 0 from the right would be a different value than as h went to 0 from the left. Now, this we commonly refer to as the right-hand derivative. So it's almost like as you're coming in from the right, what are all these slopes approaching? That slope looks like it's, I don't know, negative a half, right? As opposed to this guy right here, limit as h goes to 0 from the left, we refer to that as the left-hand derivative. All right? So as the slopes are coming in from the left, it looks like that slope, I don't know, maybe it's approaching positive 7. So positive 7 is not the same as negative a half. So when the right-hand derivative doesn't equal the left-hand derivative, then the definition of the derivative, that two-sided limit, obviously is not going to exist. So we say that's a point of non-differentiability. So that would be an example of a corner, right? There's a very common function that we deal with all the time that has a corner, right? Absolute value of x, which we know is a graph of x and negative x, right? It's x when x is greater than or equal to 0, and it's negative x when x is less than 0. If I was to sketch this bad boy here, absolute value of x looks like that. Where do you think the point of non-differentiability is, right? Hopefully you're saying at 0. The derivative is not defined at 0. This would be a point of non-differentiability. Specifically, if I classified it, it's a corner, okay? All right, we also have things called cusps. Cusps are pretty cool. So what's the deal there? How do they play out? Well, notice we're still looking at the right hand and the left hand derivative, but if one of those derivatives is an infinity, in fact, if they match infinities. So in other words, if the right hand derivative, I'm sorry, not match, duh, sorry about that, opposite infinities. So in other words, if the right hand derivative is positive infinity and the left hand derivative is negative infinity, so opposite infinities, you would get a cusp. Now, think about that, right? If I was to sketch in slopes, that's a positive slope, right? Positive, I don't know, 3. That's another positive slope. Maybe that's positive 5. As I get closer and closer and closer to this point of interest, look at my slopes. They're getting more and more positive. They're going to positive infinity from this side. So my left-hand derivative would be approaching positive infinity. If I looked at the slopes on the other side, right, that looks like a negative 2 or negative a half. This looks like a negative 2. That looks like a negative 7, right? And look, they're getting more and more negative. These slopes are approaching negative infinity. So when you're approaching opposite infinity, when the slopes, when the one-sided derivatives are approaching opposite infinity, we have a cusp there, right? Now, if we wanted to draw the picture where it was not plus to minus, but minus to plus, that would look something like that, right? Where these are all negative, these are all positive. So there you have a cusp. And then the one that I kind of just screwed up 2 seconds ago, which is, all right, what if they approach the same infinity? So what if you look at that right hand and that left hand derivative, and now they're matching infinities, right? Turns out you get what we call a vertical tangent. So think about it. If I'm looking at the slopes here, look at all these slopes. They're getting more and more positive. They're approaching positive infinity. Well, guess what? Coming from the right, these are all positive as well. So they're approaching positive infinity. So when they're both approaching the same infinity, we get what we call a vertical tangent. Now, you might be like, well, I don't get it. Like, that's nice and smooth. We're not talking about smooth here. We're talking about, slope of the tangent line. And what do you know about the slope of a vertical line? Well, in math, you learned back in the day in algebra that it was undefined or there was no slope. And that's basically the deal, right? So a vertical tangent is also a pond or a point of non-differentiability. So if you have a function, first you check for its continuity. If it's continuous and it says, all right, tell me, first find the point of non-differentiability and then classify it. Well, you really have 3 choices, right? 3 choices that we're going to discuss here. It's either going to be a corner, a cusp, or a vertical tangent. Well, how am I going to classify it? Well, look at all of these explanations. They all involve you looking at the right hand and the left hand derivative and making some sort of comparison. If they're opposite numbers, it's a corner. If they're opposite infinities, it's going to be a cusp. If they're same infinity, it's going to be a vertical tangent. All right. So now, the one thing that I asked before, maybe you had a little bit of time to think about it now that you see these different points of non-differentiability. It says if f is differentiable at a point, then it must be continuous. That's actually a theorem. So if I ever tell you that f is differentiable, well, then you know for a fact that it's got to be continuous. And the proof of that actually isn't too crazy, but we're not going to do it right now. All right, just kind of take it that if you can draw on a tangent line, that means the function's continuous. All right. The question I do want to ask you is, do you think the converse of that is true? So in other words, if you're continuous, do you have to be differentiable? And take a second, maybe pause the video and see if you can answer that. When you come back, you should be saying, no, you just showed me some examples, right? I can trace a graph like that. I trace that without lifting up my pen, but this would be a corner. It's not a smooth transition. It's a jagged turn. If you're on a roller coaster, it would be bad, okay? This is an example of not smooth or a corner as opposed to something like that, which that'd be a nice roller coaster, right? That is an example of differentiability. This is an example of non-differentiability, point of non-differentiability. So the answer is the converse is not true. So differentiability, that implies continuity, but the reverse of that is not true. All right. So one-sided derivatives. You heard me talking about them up top. So I'm just going to lay it out formally. This is basically the definition of the derivative. And if we wanted the derivative at, say, a left endpoint A, we only consider values of h that are greater than 0. So in other words, the limit as h goes to 0 from the right. And that's that same old picture that I showed you with Desmos. So as you bring in this point closer and closer and closer, you only do it from one side, you're going to get the slope of that tangent line. All right, so that would be the one-sided derivative, or specifically the right-hand derivative. Likewise, if you wanted the derivative at a right endpoint B, now you're only going to consider values of h that are negative, because b plus a negative will bring you to the left of it, right? And so as we bring this point closer and closer and closer here, you're going to end up getting that tangent line. So this is your right-hand derivative, your left-hand derivative. All right, so let's do some practice. So here we go. You ready? Show that the following function has a left-hand derivative and a right-hand derivative at x equals 0, but does not have a derivative at x equals 0. It says, therefore, or in other words, the function is not differentiable. All right, so let's do the right-hand derivative. So to do the right-hand derivative, that's simply the limit as h goes to 0 from the right of f of x plus h minus f of x all over h. Now, what is x here? I specifically am interested in this derivative at 0. So I'm not going to put in x plus h. I'm not going to get the slope producing machine. I'm just going to put 0 plus h in. So f of 0 plus h minus f of 0 all over h. And I'm going to go ahead and do this now. So first off, 0 plus h, that's just h, right? So I get f of h. The question is, I have to put h in the function f. Where would I be doing it? Well, if h is going to 0 from the right, that means h is positive. So 0 plus a positive puts me to the right of 0. That puts me on that branch there, right? So when I go to do f of h here, I'm going to get 2h, okay? F of 0, you can actually screw this up. It doesn't even matter if you're doing 0 squared to 2 times 0. That's just going to be 0. Again, I would be doing that, though, from the right. And then all over h, and then limit as h goes to 0 from the right. So now what happens here? Well, you're going to get 2h over h. Hopefully you can see, right? We'll do it nice and pretty. You can cross these out now, and you're going to get the limit of 2 as h goes to 0 from the right. So the limit of a constant is a constant itself. You get 2. So the right-hand derivative is 2. What does that mean? That means if I was to kind of trace along the graph coming to 0 from the right, the slopes of my tangent lines would be approaching 2. And I'll show you that in a second when I look at the graph. Let's go ahead and do the left-hand derivative now. Maybe we'll do a nice little bluish purple color here. So left-hand derivative. So the left-hand derivative is the limit as h goes to 0 from the left. And again, definition of derivative. It's f of x plus h minus f of x all over h. I specifically am interested in the derivative at 0, so I'm going to do f of 0 plus h minus f of 0 all over h. So now f of 0 plus h, if h is negative, 0 plus a negative puts me to the left of 0. We're now talking about using that branch, right? So I would get the limit as h goes to 0 from the left. That would be h squared, because I'm plugging into here now. Minus 0, 0 squared is 0, all over h. So now when I spruce this up, this factor of h crosses out with that. I end up getting the limit of, gotta get my cool color, the limit of h as h goes 0 from the left. Well, I just directly substitute 0 and I get 0. So this is saying that the left-hand derivative is 0. So if the right-hand derivative is 2 and the left-hand derivative is 0, well, think about it, guys. That means then that the two-sided limit, the limit of f of 0 plus h minus f of 0 all over h, as h goes to 0 from both sides, that does not exist. And oh, by the way, what does this represent? That's f prime of 0. So therefore, f prime of 0 does not exist. There is no derivative there. You can't talk about it. Like, what are you talking about? Let me look at the graph. Maybe that'll help you out. So I graphed this piecewise function. Should kind of make sense to you, right? To the left, it's the parabola x squared. Then we turn that off, and to the right, it's the line. All right, so let's go ahead and do this. Maybe I'll draw on this a little bit. All right, bust out a pen. Maybe we'll go with a nice little blue here. So take a look. All right, right-hand derivative. So the slopes of the tangent lines coming in from the right. Well, this is a line here. So no matter where I draw in these tangent lines, right, as I go to 0 from the right, all of these tangent lines are approaching a slope of 2. So my right-hand derivative is pretty clear is going to be 2. But now what about when I come from the left, right? What's the deal there? Well, this is some really big negative value. And then I come here and it's not as negative. And then I come here and it's not as negative. It's kind of remember, parabolas do that, right? And it looks like these slopes are leveling off here. So these slopes are approaching 0 down there. So they're not approaching the same thing. It's like, oh, we're leveling off here to 0 and then boop. So we have a corner. So that is a point of non-differentiability, and it would be classified as a corner. Right? It'd be a bad roller coaster to be on. You kind of get like a little jolt if you're on the roller coaster, and no one wants a jolt when they're on a roller coaster. All right, solid little question. All right, let's bring it to the next one. Very similar question. All right, we just worded a little differently. It says, does the curve f of x equal its piecewise function have a tangent at x equals 0? I also could have said, hey, is the derivative, does it have a derivative at x equals 0? Right? Both the same type of question. Maybe we'll do this one in a fancy green. Okay, so you're like, all right, so in order for me to do that, I have to consider the left hand and the right hand derivative because this function happens to be split at 0. So here we go, right hand derivative. That would be the limit as h goes to 0 from the right. It's just the definition of the derivative, but it's the one-sided limit. And it would be f of, and listen, it's not always 0 plus h here, guys. We're kind of hooking you up by doing that. It's not always that. So f of 0 plus h minus f of 0 all over h. So that's the limit as h goes to 0 from the right. What's f of 0 plus h? Well, I'm going to put 0 plus h. Now let's see. If h is 0 from the right, it means h is positive. 0 plus positive is positive. That means I'm approaching on this graph here, right? So f of h, that would be h squared minus h, right? Minus f of 0, that's going to be 0 squared minus 0. That's just going to be 0 all over h. All right, what happens here? I can either give out the lemonade, hopefully you know what that means, or up top, I can factor the h and get that. Ba-blam, super excited. All right, cross out these h's now, and now I can actually take the limit. And if I plug 0 in for h, I'm going to get negative 1. So my left-hand derivative looks like it's going to be negative 1. Okay, what would my right-hand derivative? All right, my right-hand derivative is negative 1. What would my left-hand derivative be? Well, it's basically the definition of the derivative, but just from one side. Limit as h goes 0 from the left. So same deal, still finding it at 0. But now when I go to do f of 0 plus h, if h is approaching 0 from the left, it means h is negative. So 0 plus a negative means I'm going to be negative, which means I'm coming on this branch. So it would be negative h minus 0 over h. The h's cross out. I just get negative 1. The limit of constant self. Oh, look at that. So since the right-hand derivative and the left-hand derivative are the same, then that means the limit as h goes to 0 from both sides of f of 0 plus h minus f of 0 all over h. Oh, by the way, that's f prime of 0. That's what this means. That means that it exists and it's actually equal to negative 1. All right, let's take a look at the graph. See if that seems kosher, right? If I ask you, then describe the transition. Pause the video. Think about what you'd say to me. Describe the transition. Let me turn this off. Let me go ahead and put this on now, right? So that is the negative x portion. And then this is the x squared minus x portion for x greater than 0. I put the two together. This is the graph I get. So what is happening here? You can kind of see what's happening. It's really, really cool, all right? Your slopes of your tangent lines, as they are coming in from the right-hand derivative, they're approaching negative 1. But also your slopes of your tangent lines as they're coming in from the left are approaching the same thing. So your left-hand derivative is negative 1. So when they're approaching the same thing, describe the transition right there. It is a smooth transition. It would be a nice roller coaster to be on, right? Woo, just like that, nice and smooth. So that is not a point of non-differentiability. It's a point of differentiability. So here, f prime of 0 would in fact exist. All right, pretty neat stuff. Getting into this. All right, so here we go. Let's go to the next question. Close that out. Come back here. All right, this one. It's a multiple choice question. It says, let f be the function defined below. Which of the following statements is true? This is a typical AP Calc question, right? Typical question on your exam. So when you look at these choices, you're like, all right, every single choice is talking about differentiability and continuity, right? They're all basically have some sort of version of differentiability and continuity. So what's the first thing you're always supposed to check? You don't before you even check differentiability. Hopefully you're saying continuity. So now, all right, what does this mean? Well, they're all telling you at x equals 5, at x equals 5, at x equals 5, at x equals 5. But that would be the point of interest for you anyway, because 2 is continuous everywhere. 2x minus 4 is continuous everywhere. So the only possible spot where this function is not going to be continuous is where 5 is, where they potentially meet or don't meet. So I would be interested in doing the limit of f of x as x went to 5 and seeing, do you equal f of 5? Well, in order to do this limit, I'd have to do the limit of f of x as x goes to 5 strictly from the right. So strictly from the right, I'm using this piece. 2 times 5 is 10. 10 minus 4 is 6. Then I would do the limit of f of x as x goes to 5 strictly from the left. Well, strictly from the left, I'm going to use that piece. Well, that answer is just 2. So if the limit as x goes to 5 from the right and left, if they're not the same, then that means this two-sided limit, therefore, the limit of f of x as x goes to 5, that means that that does not exist. And since it doesn't exist, then you can't be continuous. And in particular, and oh, by the way, this is review now, since the one-sided limits of the function, not the derivative, guys, of the function are different values, you should know what to expect when you look at the graph. There should be a, hopefully you say jump. All right, so now let's look at the choices. They're all f is not differentiable, f is not differentiable. All right, so but what's the reason? Well, this one says because f is not continuous at x equals 5. Well, blammo. That's going to have to be it, right? So now if we went ahead and looked at the graph, just to see what the heck's going on here, turn this off, there's the 2, there's the 2x minus 4, and you can see, oh yeah, there's a jump, right? So the one-sided limits of the function as x went to 5, they were not the same. And so it never actually met. And if you're not continuous, guys, you cannot be differentiable. You have to have continuity first. So that's an example of where you'd want to check that first. All right, let's take a look at this question. It says, which of the following statements, if true, cannot be used to conclude that f of 0 exists? So, all right, this is pretty interesting. So the first one says f is continuous at x equals 0. And you're like, how does this have to do anything with what we were doing? Well, it kind of does. I mean, differentiable is one of the choices, right? So first off, what does this tell you? If f is continuous at x equals 0, that tells you something. That tells you that the limit of f of x as x goes to 0 must equal f of 0, right? So that would have to mean that f of 0 has got to exist. So this said which one cannot be used to conclude it? Well, this one can, because this has to happen, right, in order for it to be continuous. So it ain't that choice. All right, let's skip down to this since I see the limit right here. Of course this limit must exist, right? It's going to have to. If this limit exists, does that mean that f of 0 exists? Well, that's actually a decent question. I don't know why I'm crossing it out. So, we'll go back to that. Graph of f has a y-intercept. You're like, well, what's a y-intercept? Y-intercept, what's the x value at a y-intercept, right? The x value is 0. So f of 0, right, is a y-intercept, basically. All right, whatever that value is. If it's b, right, that's going to be your y-intercept. So if you have a y-intercept, then this has got to exist. All right, so it can't be that. This guy here, this is kind of like, hey, if f is differentiable at x equals 0, we learned before that, well, it's got to be continuous then. And if it's got to be continuous, then that brings you back that this has to be true. So this has to exist. And so this was me being a little too quick there before. Just because this exists, right, doesn't necessarily mean that it equals f of 0. You can have the two-sided limit exist and not equal f of 0, right? You can have a removable discontinuity. So this doesn't guarantee you that f of 0 exists. And that actually goes back to, remember that the limit does not necessarily need to equal the functional value. So the fact that I even attempted to potentially cross that out before, I should almost, I should be punished for that. But luckily I caught it. So that's going to be your answer. All right, 5 is the last one, basically the last one. 5, it says the figure below shows a graph of the function f, which has a vertical tangent at x equals 4. All right, so you now know that a vertical tangent is going to be a point of non-differentiability. So if I went ahead and, I don't know why it's not letting me write it. Let's give that a go. Let's cross actually that out. Go back here. All right. Give it one more shot. Not let me do it. That's all right. So vertical tangent means I can draw a vertical tangent right there. So the derivative is undefined because it'd be vertical line, no slope. Horizontal tangent would mean, let's see, horizontal tangent of 5, which means I could draw a tangent line right there, and the derivative would exist, and its slope would be 0. Right? I'm trying here. I'm trying, baby. Come on, give me something. Give me something. Oh, maybe I see something there. All right, doesn't want to do it. That's all right. Okay, so now let's look at the choices. It says f is not differentiable at x equals 2 because the graph has a jump discontinuity. Well, that's true. If you're not continuous, you can't be differentiable. It says which of the following is false. So that one's true. F is not differentiable at x equals 4 because the graph has a vertical tangent. Well, that is true, right? Vertical tangents are points of non-differentiability. Okay, there'd be no slope there. So that is also true. C, f is not differentiable at x equals 5 because the graph has a horizontal tangent. That would be false because a horizontal tangent means that not only that the derivative exists, but you know its value is 0, right? Because the derivative is the slope of the tangent line, and when the horizontal tangent line happens, the slope of it is 0. So that's got to be your answer. Just take a look at D for kicks and giggles. It says if f is not differentiable, or f is not differentiable at x equals 7 because the graph has a removable discontinuity. Well, again, that's true. If you're not continuous, you can't be differentiable. All right. And then the final thing, this is just like a quick little reference here. A lot of times, especially in college, teachers or calc professors will talk about local linearity. And it's basically the same thing as differentiability. So if you use the word differentiability, you can interchange that with local linearity. It basically means that if you zoom in tight enough to any function that's differentiable, you're going to get a one-way line from left to right. Right? So keep zooming in. I tried to give an example here where here's a curve. I zoom in on this window. I get that. Then I zoom in on this window. If you keep zooming in, you're going to get a line with one slope. All right. And the slope of that line would look like the slope, or would be the slope of the tangent line. Local meaning zoomed in, linearity meaning line. When you zoom in, you get a line. So using the words local linearity and differentiability are exactly the same thing. So now it says, well, what would your calculator screen look like if you zoomed in on a cusp or a corner, which, oh, by the way, those are points that are not differentiable. So I'll let you do that. You can kind of put that in there and submit your notes. And that's that. All right, so be good.